which is given by Fermi-Dirac statistics, or this is called as a Fermi-Dirac distribution function. And we said that if you now put this free energy component in it, then we are going to get this thing. And we said that this ns will be always greater than 0 and strictly less than 1. Why? Because you know that your mean occupancy will be, so you are going to have a null spin or you will have a full spin, or case of coupled particles or paired electrons. Okay, so that is, and how this is coming? This is coming because of the Pauli's exclusion principle. Now, if we if we discuss similar now in similar fashion, if we go for this Bose-Einstein statistics, we go for the Bose-Einstein statistics. For Bose-Einstein statistics, then finally you will see that so here your mean occupancy is again this thing which we have already written. Ns bar is equal to summation over n1 n2 and so on and so forth, ns e raised to minus beta n1 epsilon 1 plus n2 epsilon 2 and so on and so forth, divided by sum of n1 comma n2 so on and so forth, e raised to minus beta n1 epsilon 1 plus n2 epsilon 2 plus so on and so forth. Okay, this will be your, it will be same thing, and then the range will be overall numbers. Okay, so n1 n1 n2, such that how many level we will have now. In this is a Bose-Einstein statistics, so there is no restriction on particle. In case of Fermi-Dirac, you will have a paired spin or unpaired, unpaired electrons. So you have this 0 and 1 value. So there are two levels, but here that is not the case. You can pair up a lot of things. You can pair lot many uh, particle, as much as in the ensemble. So just a minute, it is now hanged. I don't know. So in that case, three for each r, the situation will be different. And then this comes from the case because we are considering photons. Why? Because these photons, okay, they are going to satisfy the condition which is given by this equation, which I will show you. So let me write that expression first. Okay, so we have this n1 n2 n1 n2 and so on and so forth, where we have nr is equal to 0 1 2 3 4 so on and so forth, and for each r will be different thing. Now what thing it is going to satisfy? It is going to satisfy that this thing is equal to, this is total number of particles are given by this relation. And then if we perform same thing as we performed last time, okay, what we are going to get? You are going to get this ns will be then given by ns is equal to 0 plus e raised to minus beta epsilon s summation zs n minus 1, okay, plus 2 into e raised to 2 into e raised to 2 minus 2 beta epsilon s zs n minus 2 plus and so on and so forth, divided by zs of n plus e raised to minus beta epsilon s zs of n minus 1 plus e raised to minus 2 beta epsilon s zs of n minus 2, the so on and so forth. We call this as relation number 2. This is 1, this is 2. Sorry, this is 2, this is 3. And then we can write it like this: ns is equal to summation over ns e raised to minus ns alpha plus beta epsilon s es divided by summation over s, this will say s e raised to minus ns e raised to minus to minus ns ns alpha plus beta epsilon s, called as relation number 4. Okay, and this is similar to what we have seen previously. If you look at this, okay, if you look at this expression, this is similarly what we have written previously over here. This thing, okay. Same thing we are written for whatever is for photon gas. Same similar expressions we have written it for boson. So bosons, that's why photons are boson example of. Now only thing which is differing here is that we have written beta epsilon s. Beta, this is the only term which is different, okay, and that term over there is now replaced by this alpha plus beta epsilon. Okay, this is for photon and this is for bosons. Okay, and then the rest of the calculation is same as you have seen. And previously we have calculated this ns, okay, which is nothing but minus 1 upon beta daba by daba epsilon daba es, same thing which we have done it over here. Okay, ns is equal to minus 1 upon beta daba by daba es or epsilon is summation of e raised to minus beta ns epsilon s divided by this. So we get a expression for mean ns. Similar thing we will get, and this will yield, this will have a similar term over here except the change over here. Now we write this, so this will yield ns is equal to 1 divided by e raised to alpha plus beta epsilon s minus 1. We call this as relation number 5. And then this distribution is called Bose. The distribution is called Bose-Einstein distribution. You note here, you see carefully here that ns bar can become very large, in this case. So there is no restriction, okay. And then the parameter alpha, okay, is determined by the condition, okay, which is similar like given by summation over r of nr. All mean occupancy is nothing but total occupancy. Okay, this distribution is called as Bose instant distribution. It is saving now. Bose. Or this gas, the ensemble which satisfy this thing, okay, is called as a Bose-Einstein. Is called as boson. This is called Bose-Einstein distribution. Bose-Einstein distribution. And remember here that ns can become very large. Very large. And then the parameter, okay, parameter alpha, we can determine like similarly what we have done for over here. So alpha can be determined by summation over n of r, which is nothing but total number of particles. So this thing we can easily write, okay, nothing but we can write summation for r plus beta epsilon s minus 1 is equal to n. We will call this as relation number 6. And you know that this is again related to the chemical potential Fermi-Dirac statistics. Okay, so in that case, you know that we have written this alpha is equal to minus beta into mu. Alpha is nothing but minus beta into mu. So if you put that, we will have this ns. Okay, this ns is given by 1 upon e raised to beta epsilon s minus mu. Okay, minus 1. We call this relation number 7. Oops. And then in case of photon, the sum are to be performed without any restriction. As why? Because the total number n is the total number of particles. So that we can have Zn or Zs of n. It does not. Doesn't depend on n. And so in that case, in 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 that case, what is going to happen? Your alpha, which is equal to dabba ln z by dabba n. Okay, this is given. Okay, since is given by, this is equal to 0, equal to 0. uh, so if you see that this thing, you see this expression which is given over here. Okay, this expression, then it reduces to the Planck distribution. It reduces to the Planck distribution, which is then it will become this is equal to 1 divided by e raised to beta epsilon s minus 4. Call this is nothing but this is a Planck distribution. Okay. Now, in case of photons, okay, or other particle whose total number is not fixed, okay, this epsilon s or es, you can call it epsilon s. Uh, it is defined by the energy necessary to create one particle in state. So now, for example, if you have epsilon s, omega is the angular frequency of the photon, and you suppose that this energy scale is shifted by an arbitrary constant eta. Okay, so that the ground state of the photon gas, okay, you have this, where you have this situation n1 is equal to n2 is equal to n3. Okay, all this is equal to 0, has energy eta. This has energy eta. Okay, instead of the 0 energy. Then the energy of the gas in that particular state is simply given by E is equal to nr epsilon r plus eta. So it is as simple. It is just an additive constant. It is just an additive constant. But now, if you now this arrangement make it very trivial. Why? Because if you see our previous relation first, which we have written, mean occupancy relation. Okay, this constant eta straight away get cancelled. Okay, and your Planck distribution so what you are going to get, you are going to get a Planck distribution. So your Planck distribution is not going to get you are not it is not going to be affected. So this simple arrangement in our epsilon r, I have given this as an exercise to look into, okay, in my notes, and then you have to do it. Just a minute, it's saving now. This nr epsilon r plus eta. Okay, and then our first, if you see this first expression which I have written over here, in this thing it simply get cancelled, and then you will have same distribution. So Planck distribution is unaffected. Okay, so Planck distribution is unaffected. So, but in case of ordinary gases with a fixed number of particles, epsilon at s will denote the energy level of that particle in a particular state. Let us say that now it is in S state, and you suppose that this energy scale is shifted by an arbitrary constant, then all single particle energy levels are shifted by some constant eta dash. Okay, and the energy of all state of the whole gas is shifted by a constant which is given by eta is equal to n into eta dash. Okay. And once again this additional constant get cancelled, so as we see, and that's why this Fermi-Dirac and Bose-Einstein distribution are properly unaffected, or they are called as the eigen distribution. Okay? They are unaffected by this shift, so that's why they are called as the eigen distribution. Hmm? So this completes our discussion, particularly the essential feature of the quantum statistics of the ideal gas. So what we discussed thing about the quantum statistics of an ideal gas. So all these things, what is meant by ideal gas? In gas, so in that the interparticle interactions are neglected. Interparticle interactions are neglected. This is what is called as ideal gas. Interparticle interactions are neglected. But there are cases, okay, there are obviously routine cases where we can deal with the distribution functions, okay, and also thermodynamic functions like entropy, where you will have fluctuations in the statistics. You have fluctuations in NS bar. Why these fluctuations are there? These fluctuations are there because of the interparticle interaction, and then uh, in that case, what is going to happen? Your partition function z, which is of interest, will become an explicit expression z in terms of the energy level of the single particle. Here, what is happening? Since interparticle interactions are neglected, the whole system can be assigned to a level 1. Whole system can be assigned to a particular level S, NS, okay. And then, so it becomes like an energy level of the single particle. Hmm. But in case of the realistic situation where we have this interparticle interaction, each will have new level generation. Okay? Each will have a new level of generation. So that's the thing which is different in case of the realist. So it's a, then it will be a quantum statistics for an real gas. So what will be the situation? It will be the quantum statistics for real gases. Okay? Real gases. But we will at present we will not. It will be very difficult, cumbersome for you to have these calculations to be seen right away. Instead, what we are going to do, I am going to show you, is the very applied thing, application of this Fermi-Dirac statistics, application of Fermi-Dirac statistics to, or Fermi-Dirac function to electrons in metals. Electrons in metals. Now, in solid state physics, you might have learned in solid state physics, you might have learned that in metals core ions can be neglected. Core ions can be neglected. What does that mean? We are going to see now. We are going to see now. Just a minute. Metals. In metals, as a first approximation. So in metals, first of all, uh, just a minute, it is saving now. In metals, you can neglect core. Core means positive ions. So if you have metal, let me say that this is a metal, and then if you have this positive ions, which are sitting over here, then then these electrons are embedded all over. Electrons are embedded all over this core. And then as a so this is my iron core, and this is my electrons. They are so high, and we can neglect their mutual interaction. So what we are going to do, we are going to assume that we'll neglect electron interaction. We are going to neglect, okay? And then we are going to neglect their mutual interaction, okay? And then these electrons can be then treated as an ideal gas. So such thing can be treated as an ideal gas, and then their concentration in metal, although is very high, okay, even at ordinary temperature, by an approximation of the classical statistics, uh, we can appropriately apply Fermi-Dirac statistics, okay, which we just now discussed yesterday for the conduction electron momentum. And then in that case, what is going to happen? You know that we have written this expression. We have written this expression. We have written this expression. Ns mean occupancy is given by 1 divided by e raised to alpha plus beta epsilon s plus 1. Okay. Yeah. We wrote this expression, and one can find that the mean number of particles in a state S for the Fermi-Dirac distribution function Ns will be then simply given by this thing, which is equal to 1 divided by e raised to beta epsilon s minus mu plus 1. Call this is relation number 1. This is relation number 2. And then by definition we have this mu, which is equal to minus alpha upon beta, which is equal to minus k t alpha. Call this as relation number 3. And then this quantity mu is called as the Fermi energy of the system. Called as Fermi energy of the system. Okay. And incidentally, we have already seen that this thing previously, that mu is also called as the chemical potential of the gas. Mu is also called as the chemical potential of the gas. So we have two things. We have Fermi energy and we have chemical potential. So now they started become competing each other. They start competing each other. So how this chemical potential is given? This chemical potential, if you see our previous expression, this chemical potential is given by, remember our expression F is equal to minus kT ln of Z, where F is my free energy, and then I can express this free energy in terms of alpha. How we expressed it? You remember last time we express it in terms of alpha is equal to minus 1 upon kT di by F by di by n, where T is my absolute temperature and N is my number of particles, total number of particles. And then if we write that, then it is nothing but it is a ratio of mu to upon kT or beta mu. Okay, so let me write it. Write it. Alpha is equal to minus 1 upon kT di by F by di by n, which is equal to minus mu upon kT, or which is equal to minus beta mu. And where mu is called as the chemical potential. The parameter alpha or mu can be determined by this condition: alpha summation over n ns bar is equal to summation over s e raised 1 upon e raised to beta epsilon s minus mu plus 1 equal to n. Where n is number of particles in volume V. And then we have used this equation, which equation? We have used this equation, above equation, let us call this relation number 4. Okay, and mu is then a function of the temperature, and then this behavior we can write. So we can write this as f of epsilon, which is equal to 1 divided by e raised to beta epsilon minus mu plus 1. Okay. We call this as relation number 5, where this f is called as f of epsilon is called as Fermi function. Fermi function, and then it has a function of epsilon because it's a function of epsilon energy. And then this energy can be measured above the lowest possible value of epsilon is equal to 0. Okay? And if mu, you set it such that beta mu is much less than 0, okay, then we will have this thing e raised to beta epsilon minus mu. Why? Because then this will become very high as compared to 1. Okay? And then this Fermi function reduces to the Maxwell-Boltzmann distribution. So this Fermi function reduces to Maxwell-Boltzmann distribution, and then in case of free electron Fermi gas or free electrons in metal, we are interested to have an opposite limit where we have beta mu, okay, which is equal to nothing but mu upon kt, okay, which is very very high as compared to 1. So this mu is very dominating as compared to kt. So that's the thing. Now in this case, if the epsilon is very small as compared to mu, then this beta epsilon minus mu is very very less as small as compared to 0, so that you will have a f of epsilon is equal to 1. On the other hand, if epsilon is big as compared to mu, then beta epsilon minus mu, okay, is very high as compared to 0, and in that case your f of epsilon, okay, will become e raised to beta mu minus 0, okay? And then it will fall off exponentially like a classical Boltzmann distribution. Okay? So it will, so this will fall like a Maxwell Boltzmann distribution. And what will happen if f is equal to epsilon is equal to mu? Then we'll have Fermi value, Fermi function to be f. We'll have Fermi function to be half. So what will happen? It will have epsilon is equal to mu, and epsilon minus mu is 0, e raised to 0 is nothing but 1. And then this year f of epsilon will become half. Okay? And so the transition region in which this f goes from a value close to 1 to a value close to 0 corresponds to an energy interval of the order of kT, about epsilon is equal to mu. I will show you in figure how this happens. So if you have, if epsilon is equal to mu, then f is equal to half. And then if you want, if I plot it, if I plot f of epsilon as a function of epsilon, okay, we have 0 to 1, then here you have occupancy 1, and then it will fall off, as I showed you previously also, like a cumulant. And then in that case, this is half. And then this is my chemical potential. This will go, this will change of the order of this change is of the order of mu, and then this mu is nothing but 2 kt. Okay, price of kt. So the transition region in which this f is going close to 1 to a value close to 0, okay, it corresponds to the energy interval of the order of kt or 2 kt. The 2 kt, 3 kt doesn't matter much. Total, so half kt, this its total width will be given by 2 kt. Okay, and so ideally, so if you so in case you know, when in case of limit when t tends to 0, so in case of limit when t tends to 0, first of all let me draw the ideal case. Okay, So this is like a finite temperature, and then for so this is like a T is equal to finite. Finite. Why? Because as T tends to zero, as T tends to zero, okay, or let us say beta tends to infinity, okay, this transition region become infinitely narrow. This is going to become straight. So how this will look like? This will look like something like this. And same thing, epsilon and some sort of f of epsilon over here. This is zero. Same thing which you will see over here. And now here, instead of this wiggling distribution like Maxwell-Boltzmann, you will have things like this. Where in mu, okay, here then mu, okay, what will be the value of mu then? So in that case, the transition region become infinitely narrow, and then in this case, your f become one. Your f become one for all the f of epsilon is equal to one for epsilon less than mu, okay, and f of epsilon is equal to 0 for epsilon greater than mu. Okay, and then this is, and you can see this is a obvious result for the absolute zero situation where the gas in its ground state of lowest energy. Now, since we have this exclusion principle that requires that there is no more than one particle per single particle state, the lowest energy of the gas can be obtained by piling up the particles into the lowest available unoccupied state until all particles are accommodated. Okay, and then the last particle that can be added or to the pile has quite a considerable energy mu. Why? Because since all the lowest energy states have already been filled up. Okay, so one can see that this exclusion principle implies that this Fermi Dirac gas, has a large mean energy even at absolute zero. Right? Now one can calculate Fermi energy. We can calculate this Fermi energy at mu is equal to mu zero of a gas at T is equal to zero, and then energy of each particle. Now how this can be calculated, because you see now we are talking something about T is equal to zero, we have momentum is equal to zero, and then can we have momentum of the particle to be zero? You remember my argument last time which I have done over there. What was the argument which I have done? We have a particle at any instant of time, we have a wave function associated, or in language of statistical mechanics, this is its position is given by some distribution. Similarly, its momentum is given by some distribution. But now we are coming to a point where we are saying that we have this zero momentum kind of thing, or particle as a energy of the particle has a zero momentum. Okay, because why we are now we are going to this type of thing. And now then how to express it, or what is the physical consequence of this thing? So now let us try to calculate it using the class statistical ensemble approach which we have. And now let the energy of each particle is related to its is given by its momentum, which is given by P is equal to h cross k. So how the energy will look like in that case? So let us, what we'll do is that let's calculate Fermi energy. Let's calculate Fermi energy mu equal to mu zero, okay, for a gas at T is equal to zero. and then the energy of each particle is then given. How the energy is given? By P bar is equal to H cross K bar. We will omit this thing. I will only write the vector scalar notation. P is equal to H cross K. And then how to write energy surface? Energy is given by P square upon 2m, which is nothing but H cross square K square upon 2m. And at T is equal to 0, at T is equal to 0, all states of lowest energy are filled up to the Fermi energy epsilon, which corresponds to the Fermi momentum. And then it has a magnitude. It has a magnitude Pf. Fermi momentum Pf is then given by Pf is equal to H cross Kf. H cross Kf. Such that how this is, such that you have this mu 0 is equal to Pf square upon 2m, which is equal to H cross square Kf upon 2m. Thus, if you see at t is equal to 0, all state at t is equal to 0, all state with k less than kf are filled, and all those states, so these are filled, and all those states with k greater than kf, okay, are empty. And then if you want to calculate the volume of such situation, the volume of the sphere with radius kf, so let us construct a volume. So we have x k1, we have a sphere, we have this kf, and the volume of the sphere with radius kf in k space, of course we have to do this constructed in k space, is given by, this volume will be given by v is equal to 4/3 pi kf cube. But if you look at this expression, uh, if we have this expression, just a minute, where is that? If you look at this expression we have written previously also. Just a minute, this is kind. So this is given by this, and a so if you see this expression which we have written previously also, rho, So this, so if you remember that we have this expression rho density of state in k space, okay, is given by v divided by 2 pi cube p d cube k. Okay, and so by virtue of this expression, there are 2 pi raised to minus 3 into v, these many states, okay, translational states per unit volume are available in k space. Okay. And then the Fermi sphere of radius k contains therefore 2 pi raised to minus 3 v into 4 third pi kf cube translational state, and then the total number of states in this sphere is 2 times as large, since each electron will have a half spin. Okay? Each electron will have spin half. Okay? Will have a two times more translational state. Okay, and then so the total number of states in this sphere is 2 times, hmm, because each electron is having a spin half thing. So we'll have, actually in principle we'll have these two spheres. We have these two spheres plus half, and then this is minus half, 2 times. But the total number of states in this sphere must be at t is equal to 0, because at t is equal to 0 you will have a perfect occupancy, and then it will be, this will be then given, this total n will be then in that case will be given by 2 into v divided by 2 pi cube into 4 third pi kf cube, which is equal to n. And then, so in other words, we can write this kf is equal to 3 pi square n by v raised to half. Okay. So naturally, when you write lambda f, not n lambda, partial, and then naturally the de Broglie wavelength, lambda f Fermi wavelength, is given by 2 pi divided by kf, which is equal to 2 pi divided by 3 pi square s to half into v by n s to half. We call this as relation number 5. And this means that this de Broglie wavelength lambda f corresponds to the Fermi momentum, uh, which is of the order of the mean interparticle separation, which is given by v by n raised to half. And then all particle state with de Broglie wavelength lambda is equal to 2 pi k raised to minus 1, okay, must be greater as compared to kf. And then these are occupied at t is equal to 0, and all those with lambda less than lambda f will be empty. Okay? This is occupied. So if you see this expression mu 0, expression for mu 0, which we have written above, over here, there is the expression gone. Anyway, we write this expression mu 0. We have written it somewhere. Yeah, over here. Yeah, mu 0 is equal to h cross square kx square upon 2m. This expression will then become h cross square upon 2m 3 pi square n by v raised to 2 by 3. Okay, so that's the chemical potential of your that's the chemical potential of your Fermi gas. Okay, the chemical potential of your Fermi. Last, just let me see, let it get saved, and I will write that last expression. Next time we'll see what is the mean energy and specific heat of this Fermi gas, free electron Fermi gas, and how this CV will vary. Okay, that's the thing which just a minute, just 1 minute, just finish off with writing this, that expression. And in that case, it is given by mu 0 is equal to h cross square kf square on 2m h cross square on 2m. Yeah. Then mu 0 is equal to h cross square upon 2m kf square, which is equal to h cross square upon 2m 3 pi square n by v raised to 2 by 3. Now you can numerically calculate. So if you have Fermi energy, if you want to calculate Fermi energy at T is equal to 0 for copper, a typical metal, and whose density is given, we will see this example. How much should be the mu 0? Okay, this is the expression. Now we next time we'll see more about this specific, especially specific heat at constant volume. Okay, and then how n changes with T specific heat. Okay, and then how this specific heat is connected to the temperature. These are the things which we'll talk about. So we'll see it tomorrow next time. Okay, we'll see it tomorrow. Hmm? Anyone is having any question? If there are no questions, then we'll stop for today.
Hello, sir. Sir.
Yes. Who is this? Any questions?